you for having me here. So today I'll be speaking of the autonomy or reinforcement learning in robotics. Specifically, we're going to be looking at Hindsight Experience Replay, HER so-called. So first of all, before diving into my presentation, just let me introduce myself a bit. So my name is Norio Kosaka. I'm doing a postgraduate student of machine learning in the UK. And my research interest is on reinforcement learning, as you might guess. And also, I've been doing an internship at this great company named the Construct since this April. So this is today's agenda. So we're gonna be looking at profile of paper and abstract, what it does, and uh, why we've developed the algorithm by ourselves, like HER. And also, this is the more important topic, but we're gonna be looking at how we could have our projects and also the hands-on parts of HER on ROStos, like how to launch, how it works, and what should we do to have our tailored own projects. And conclusion. So okay, so let's look at the profile of paper. So basically, the all authors are coming from OpenAI. So they published this paper at 2017, and the paper itself is paired with the offshore video. So if it's of your interest, maybe you can refer to the offshore video. Just click this link. Okay, so let's dive into the abstract. So in this section, I'll be explaining what it does briefly. And maybe I might skip some mathematical concepts, but you could get some firm understanding on this algorithm. So basically what it does is, as you can see, this guy is a fetch robot. It's got the end effector and arm, several joints. So in this algorithm, what we need is we won't move this guy to the desired position, which is this one, this red circle or the red cube on the table. So in the paper, they have examined their algorithm on 4 tasks: reach, pick and place, and push, and also the uh, sorry, I forgot the last one. But anyway, this is the push task. So what we have to do is we have to hit this puck and move it or the stops at this within this threshold or the region. So the reward in this case is just it just tells us if it succeeds or if it fails. So that's the basic the problem setting of this paper. So as you know, reinforcement learning has gained a lot of popularity in recent years due to some spectacular successes such as defeating the Go player and also the winning matches against the top professionals in the popular online games named StarCraft. But in most cases, the algorithm requires us to provide the configured reward function. That plays the key role. So as I explained, in our setting, we don't need such a engineered reward function. It rather tells us success or failure. So in the case of success, we get 0 for reward, and in the case of failure, we only get -1. So it's too simple binary. It doesn't tell us how much you have been doing well. And the HER algorithm or HER underlying algorithm is DDPG, which is another algorithm. So to understand this, maybe you might need to check this paper published by these guys at 2015. Yet the authors propose some strategy which allows us to append some hallucinated or the fake transitions by modifying the goal according to some future transitions in the same episode. So at this point, episode means a sequence of execution of action. So the episode starts at you initialize the simulation and then it ends at getting some results like reward -1 or 0. Okay, and by introducing the margin trajectory to our replay buffer, we ensure that no matter how bad our policy is, it will always have some positive rewards to learn from. So this guy can learn from even failure, not only success. That's the beauty of this HER. Okay, so now I'll be explaining why we've decided to develop this algorithm by ourselves. Like Ricardo explained, we could use the open source repo named baselines. This one. So it's accessible basically for anyone. But in our case, we didn't use this because mainly they've used the Python 3, which is not compatible to operating on ROS, not ROS 2. So we didn't use baselines. Rather, we've decided to develop the algorithm by ourselves. Okay, so now let's look at the practical parts of this speech, which is hands-on HER on ROS-DOS. So in this section, we'll be looking at how we could, we'll be looking at how it works and also how we can make it our own project. What these steps involved is quite simple. Only 3 steps: activate Python virtual env and also launch the shell and Gazebo window, and then launch the project. So let's try one by one. So first you have to open the shell, and also you need to open the Gazebo. Okay. And first, what you have to do is move to the Katkin workspace and then go upper directory. And at this point, you must have Python. This is the virtual environment. So we're gonna be activating this guy through this command. So in this environment, in this Python environment, since we wanted to avoid installing a lot of packages, a lot of extra packages to the native Python, because on the shared server, maybe administrator do not want you to, install a lot of things individually. So that case, it's better for us to have our own Python virtual environments. So we've done that, and this environment includes TensorFlow, not GPU, because HER doesn't require to use GPU. But anyway, we installed TensorFlow, and of course the TFRL, which is our repo to implemented the reinforcement learning bunch of algorithms, blah blah blah. Anyway, first you need to activate, and then you will launch the project with this command: ROS launch space fetch OpenAI ROS example space start HER reach, because for now we're gonna be looking at the task of reach. Okay, reach is you try to stretch your arm to the desired position. Okay, so let's have a look. Of course, I'll be explaining what it does deeply after, but for now, just see, try to make it work on your environment. And at this point, you might get some error, but I am sure if you try several times, it will work. Okay, if it doesn't work, just leave the comment on the chat. We're gonna be investigating why it doesn't. Yo, there you are. So we have this is the it looks simple, but this is our simulation environment. Okay, so we try to hit this cube by this arm while it's moving around, and it of course this is the AI stuff, so it might take time to learn. Okay, so let's just leave it. Instead, jump into the looking how it works. Okay, so in this section, I'd like to briefly explain how it works and what to do to make it your tailored project. Basically, this project stands on several other packages, so that we have to carefully modify each path to have our own project. So let's have a look at the organization of the whole project first of all. So if you open the IDE and then open up this IDE in another tab, okay. You will be looking this organization. So I'm going to briefly explain how what is the content of the source code. Okay. So first you open or you expand Katkin workspace, go to source, and at this point we have two packages. First of all, okay, this is the examples project which we've launched, and this is the core package which maintains the robot in general on the simulation. Okay, so let's look at what it does. The training script. Okay, so by training script, what I meant is, this is the simple organization of the OpenAI ROS. So we have training script part. This is what we need to create. It's not given. So we have to create training script. And besides, we have task environment, robot environment, and Gazebo environment. So basically, this task inherits these superclasses. Okay, so when you launch this training script, it's going to launch tasks and launch robots and Gazebo, and you will have fetch robot in the simulation. But the basic um, interface provided us from Gazebo environment. So what you might need to understand is Gazebo environment, and then you could go robot tasks and training script, have your own training script. But for now, let's just go like reverse way, like we did launch. So this is the launch script actually, and this is launch file. So it's looking quite simple. We launched the parameter server, which is this YAML, and also we have launched the training system, which is this HER reach by. It's in the script directory. And inside HER reach, what it does is first, we are using TensorFlow Eager. Maybe you might know PyTorch or other deep learning libraries. Eager is one of the newest features provided by Google. So with this Eager, what we could, or Eager enables us to access Tensor, the content of Tensor, without using session or session.run. So one of the things barriers us or prevents us from learning or the starting to learn TensorFlow was session. Session was the like huge monster in terms of learning. So using Eager, we could easily access the content of the Tensor. Okay, so first we activate Eager, and then we're gonna give the parameters, and also we need to get a goal. In this case, goal means the goal of this simulation. It's not the desired position. Okay, like the final outcome, what we expect, and the number of test episodes, and we're gonna be creating the log directory or model directory to save the models. And this is the important line, which I'm going to explain later. But anyway, at this line, we invoke the environments. So this environment has several APIs, like a step, reset, and close. So that's being implemented this OpenAI ROS, which provided by the Construct, this company. So in this training HER script, of course, I'm not going to explain the detail of this training script, but inside this API, agent interact with environments and then get some observation and then decide on the specific action, execute it, and then get reward and learn from it. Okay. So that's the training script in nutshell. Okay. So we've looked at this part. So this is what we have to create. And next, we're gonna be looking at what we are given. Okay, so this OpenAI ROS contains the several additional packages, robot amps, task amps, and in the robot amps, we have fetch amp in this case, and also the task amps, task environment, we have fetch reach. So in the fetch environment, we have the base class maintains the fetch robots and the organizes the classes below, like object position. This object means the cube or the desired position. So through this class, we have access to the basic properties of the cube or red cube, like you saw in the Gazebo, red cube of the properties in a simulation. So you could initialize randomly initialize the position of cube, or you could get the 3D coordinates, XYZ coordinates in Cartesian space. And also we have, this is one of the most important class, which actually executes the action for the end effector. Execute means you move the end effector to the position. So that's what it does. Okay, so move fetch class organizes the getting action and then executes the end effector and then renders it on the Gazebo simulation. Okay, so now we are going to look at task environment because this is the second things we have to understand. So in the task environment, basically, okay, let's actually look at that. So go to OpenAI ROS and then, yeah, one more OpenAI ROS and then source. And at this point here, as you can see, robot env or task envs, and go to task envs, and then, yeah, we've already implemented a lot of, environments already, but for now, what we need is fetch. So you go to fetch and config this config file for the fetch robots, not for the training script. So maybe you might not need to, I mean, you'll need to modify this to have your tailored own task environment. But for now, we're going to be using just fetch reach, the default one. And this is the fetch push task environment. Okay, so inside, like I mentioned, we have class for fetch reach environment, and also scroll down a bit. Oh, sorry, it's in the it's in the robot environment. So those stuff, yeah, was in the Sorry, silly me. So those stuff was implemented in the robot environment, fetch env. So just sorry, be patient a bit. So I'm gonna explain a bit of fetch reach environment for now. Okay, so this is a fetch reach environment. So in fetch reach environment, of course, we inherit this fetch environment implemented in the robot environment, and of course the utils. And when you instantiate this guy, okay, this guy will be instantiated when you, at this point, when you launch the environment through this API, start OpenAI ROS environment, you actually launch the this fetch push, and this fetch push launch, fetch reach, and this fetch reach launch the robot Gazebo environment. So that way you can launch the sequence of the required file that way. Okay. So anyway, what it does is first we're gonna ROS launch the simple world. World is the simulation. So you have fetch robot and then the table and the cube or the desired position. And using this API, you could get parameters. You could load parameters. Sorry, and then you have specified the observation space. Okay, and this is one of the most important parts, which is even explained in the notebook. So this defines the possible range of movement of end effector, because on the table you don't want him to excessively stretch out the arm. I mean, you don't want to break this robot. So somehow we have to put the constraints on the possible movement of end effector. If it's going too much further, like far away from the table, we should stop it. So that's the point of having these parameters. Okay, so I mean, to get these parameters, you have to do some experiments. Experiment in a sense, you actually send a lot of data like actions, trajectories, and then see how much move it package can enforce enact the action on the robot. And these values we've confirmed empirically. Okay, that those are valid. So self x mean, x max, y mean, y max, and that is the height. Okay, so within this like region, fetch robots try to perform the action, and then the learns from it. And so threshold is the since the target desired position is just specific like a point mass in the Cartesian 3D XYZ Cartesian space. But it's hitting that specific position is quite hard. So instead, we've decided to have a threshold. Even OpenAI Mujoko has the same threshold. So if the reach like end effector reaches at within the region defined by this threshold, then we consider that episode has been like achieved. Okay, and also yeah, most we have random. We need to randomly initialize the position of the desired position. So using this API, like a NumPy random uniform, you could get the random value within this range. Okay, so these values are used at this point, and this guy provides x, y, z coordinates to reinitialize the position of desired end effector, so desired position. Okay, so at this point you might wonder. I mean, I know you can't wait anymore to have your own project, but let's just briefly understand what is the basic framework even provided by OpenAI. Okay, so this is the basic usage of OpenAI interface, which is called GYM, just GYM, GYM. So in our case, we have to using this API, we have to launch the environment at this point, and then inside this for loop we have 20 episodes. We're gonna go through 20 episodes, and then each time we reset the environment and it gets the first observation. And the format of observation, maybe you might wonder, which is the observation itself. Okay. Well, yes, there you are. So this API provides us the actual observation. So observation itself contains, yeah, it looks a bit overwhelming, but it contains 1, 2, 3, 4, 5, 6, 7, 8, 9, or about 10 different properties about robots and also the desired position. So this is the observation, okay, like absolute position of gripper, one end effector, and objects, and also the relative position from the gripper. And also we need to check the gripper states. This gripper states about the, how do you say, the fingers, the distance of fingers. But in this case, push in the task of reach, we don't need to change the fingers. It's rather being fixed, okay? Because we don't need to pick, or we don't need to use fingers, so it's being fixed. And the rotation of objects, positional velocities of objects, and the rotational velocities of objects, and distance between fingers and velocity of grippers. Yep. So these values are coming from the observation, and achieved goal is let's go back a bit. So achieved goal is this one, achieved goal, what you have, like where you are, okay, compared to the desired position. And desired goal is the actual goal, what we aim to achieve. And each episode, for the brevity of explanation, we just only go through the 3 steps. Each step you're getting action, and then pass it to the environment step API, and as a return we could get observation, this format, and reward, which is the binary. So either it tells us either 0 for success or -1 for failure, and done is done if you it indicates if you finishes the episode. And information, yeah, information is, I mean, sorry, information is the information about the robot, so you might not need it. And after you finishes the episodes, you have to clearly close the environment. So at this point, you can shut down everything and then leave the simulation. Okay, so even this interface has been used on the documentation of OpenAI GYM. So in their case, they have to import the GYM, which is their library, and using gym.make. This is in our case, this one started start OpenAI ROS. So using this API, you could instantiate environment, and then the subsequent part is the same as ours. So environment reset, and rendering is render the image on the another window. So if you put this, you're gonna be opening another window to see the actual simulation. But in our case, we've already incorporated this and rendering function inside, so you don't need to actually do this. Okay, I mean you shouldn't do this. Okay, so environment.step at this point, like I mean you can guess the same interface, provide action and then get observation, and that way you can do the simple experiment on this cardboard. Okay. Anyway, this is the basic framework, like how you interact with the reinforcement learning through our API or through the interface of Gym. So now I'm going to explain what exactly do we need to have our own project. Yeah. So at this point, assuming that we would like to deal with some new tasks on fetch robot, or of course you can introduce your robot. So that case, you have to, I mean, you need to pay attention to the interface of robot environment and to task environment. If it's not aligned, your task environment or the learning does not, I mean, it's not gonna work, isn't it? So the procedure itself is quite simple. First, you create a task environment. This will be launched by API of start OpenAI ROS environment, like we have seen. Sorry, it's being defined in the OpenAI ROS this script. Of course, I'm going to explain later, so just be patient a bit. Let me stay on the topic. Okay, register it to this new task environment to the OpenAI ROS task envs and this env list. This is the it's like a pitfall. If you forget register your task environment to the this task list, you are not able to instantiate your simulation. So do not, I mean, do make sure, double check you have your own project and also the path to the project. Okay, and next you have to create a training script with a launch file, and at last you can just rebuild a project by cutkin make, or you can do cutkin space build if you want, and then they source it by source development slash setup.bash. Okay, so let's look at how we can do that. Okay, so far we have explored what the task environment, but besides we need to understand the robot environment. So this is the actual interface. This guide provides us actual interface like we saw, step and reset and close. So other APIs starting off other APIs names the starting with the underscore. It's not exposed for us, so you don't need to care. It's just you don't need to check it as it is. So what we need to do check is step reset close, and in the step this is the actual API which execute the action set action, which is defined quite below the set action. I mean, which is the empty for us to have it on the task environment. Okay, so in task environment you have to define how we want to how we want to execute the action. Yeah, so here it is in fetch push in a task environment script. We need to define how we want to, I mean, given the action, how we want to execute the action. So at this point, push or reach, it doesn't matter, but uh, we don't want to move the fingers. Finger has been rather fixed, so you don't need to do anything. So at this point, we unpack the action in the position control, which is the end effector of XYZ. And the last element of action is for the gripper control, okay? And we want to limit maximum change in position as in OpenAI Gym, and gripper control for the both fingers. And also at last, we want to construct the actual action. So at this point, using this NP, we concatenate everything we are given: position control X, Y, Z, and self rotation control. This was one of the pitfall for us when we developed this software, since the rotation of end effector must be fixed. So we did hard coding. This is our empirical results, how we could appropriately fix the rotation of end effector. Okay, so you don't need to, maybe you might not need to change it, or if you want to rather have your own task environment, you might investigate how you could, what is the appropriate rotation. So in this case, rotation is rather end effector is rather looking down and then fixed. Okay, so let's go back to set action. Yes, there you are. Okay, so with this action, you can pass it to the set trajectory EE. This is defined this intermediate fetch environment. So this is the robot environment, not Gazebo or not task environment. This is the given by us and the robot environment. So through this set trajectory EE API, you can actually set the position X, Y, Z, and also the rotation X, Y, Z, and W, and also gripper control to send this geometry message to the uh, move it package. So move it package based on will be executing the action or this trajectory based on this given message. So we pass this variable named EE target to the trajectory processing. Okay. So like we saw, since we want to limit or we want to put a constraint on the possible action, at this point we will be using this X, Y, Z min and max to actually clip the value. So using this clip, you can limit or you can make sure the data falls into specific range. Okay. And yep, there you are. So after that, you could get the processed E target, and then you just pass it to the move fetch object E trajectory. So this move fetch object is okay, like I explained, it organizes or yeah, there you are. Move fetch. This guy is managing the all like interface to execute the action. So this guy inside, this guy has the move it the packages, and then those have been instantiated when you launch the simulation. So you might not need to concern. But what we need is what we are doing is we actually pass the action to this guy and then execute. Or before execution, we have to plan how we could, kinematically speaking, how we could achieve that specific position with our end effector. So using this class, we can execute the action, and then yeah, uh, in the superclass we have defined what is the reward. In the task environment, we have defined what is reward, and if it's we can detect if it's ended, like if it's done or compute reward. Like I explained, reward itself is this has to 0. Okay, sorry, -1. So 0 for success, -1 for failure. Okay, and that's it for explaining the task environment and the other environments. So maybe at this point you might wonder, yeah, you can't guess we've understood everything, but of course you might have some, like when you actually developing some environment, you could have some errors. That's how software engineering goes, right? Okay, so yeah, thank you for your time, and that's it from us today. I hope you feel better and more confident on having your own projects related with reinforcement learning in general. Because as far as we've followed this simple interface, meaning environment, instantiate environment, and then through these APIs, M step and M close, basically you can I mean, in theory, you could apply any kind of reinforcement learning algorithm. Most of the reinforcement learning algorithm which aligned with the OpenAI GEM interface, you can instantly apply those algorithms to our project. So that's the beauty. Try to keep catching up with this beautiful interface provided by OpenAI GEM and implemented by us. Mm. No, thank you for listening. That's it from us.